I'm presenting a question about using Sklearn's linearregression model to predict house prices based on their size. Let's see if you can solve it. I've trained a linear regression model in Sklearn to predict house prices. The model's intercept is 50,000, and the coefficient for house size is 100. Now, I'll give you some statements to evaluate. The equation shows how the model works. Predicted HOUSEPRICE equals 50000. The base price. Plus 100 times the HOUSESIZE. It is a simple linear equation. This is the summary of the model's parameters. We'll use these to check the statements. The intercept, 50,000, represents the predicted house price when the size is 0. The coefficient 100 represents the increase in predicted house price for every 1 unit increase in house size. The intercept value is 50,000. This means the model predicts a base price of $50,000 even for a house with 0 square feet. The coefficient for house size is 100. This means for every additional square foot, the predicted house price increases by $100. This is the title of the problem. I'm using a linear regression model, a common tool in machine learning, to predict house prices. It's like drawing a straight line to best represent the relationship between house size and price. Here's the core question. I have to choose the true statements about the model I've built to predict house prices based on their size. Sklearn is a popular Python library for machine learning, and linear regression is its tool for building linear regression models. I'm using it to find the relationship between house size and price. The model gives me an intercept of 50,000 and a coefficient of 100 for the house size. These numbers define the straight line. This statement checks my understanding of the intercept, which is like the starting point of the line. If I plug in 0 for size, I get the intercept value, 50,000, as the predicted price. This tests if I understand how the coefficient affects the prediction. The coefficient, 100, tells me the price increase per extra square foot. Therefore, an additional 100 square feet increases the predicted price by 100 times 100 equals $10,000. This is about the fundamental assumption of linear regression, that the relationship between variables is a straight line. That's what I'm working with here. This statement checks my awareness of the limitations of linear regression. Linear regression models are simple, but can be strongly influenced by outliers, which are unusual data points. This statement is untrue because linear regression struggles with the unpredictable effect of outliers. I'm using the Sklearn library, a popular tool in Python for machine learning, to build a model. This specific model is a linear regression, a type of model that finds the best fitting straight line through data points. I'm using it to predict house prices based on house size. It's a great starting point for understanding prediction models. I've trained my linear regression model, and I got these results. The intercept is 50,000 and the coefficient for house size is 100. Now, let's see if you understand what that means. This statement checks our understanding of the intercept. The equation for a line is typically written as y equals mx plus c. In linear regression, the intercept, c, 50,000 in this case, is the predicted value when the predictor variable, x, is 0. So, if house size is 0, the model predicts a price of $50,000. This tests our understanding of the coefficient. The coefficient, m, 100 in this case, represents the slope of the line, indicating how much the predicted price changes for each unit change in size. An increase of 100 square feet leads to a price increase of 100 times 100 equals $10,000. Linear regression, by its very nature, assumes a straight line relationship between the variables. This means I'm assuming a constant rate of price increase per square foot. This statement tests whether you know the limitations of linear regression. Outliers, unusual data points, can greatly affect the line's fit and make predictions inaccurate, especially outside the range of the training data. So this is false. I'm using linear regression, a powerful tool from Sklearn, to predict house prices based on their size. Think of it like drawing a straight line through data points on a graph. The line's equation will help predict prices. This is the core of my linear regression model. I've got the equation. House price equals 50,000 plus 100 times the house size. The 50,000 is the starting price, intercept, and 100 represents how much the price increases for each extra square foot, coefficient or slope. It's a simple formula that shows a linear relationship between house size and price. I'm presenting a multiple choice quiz to test your understanding of this linear regression model and its parameters. Let's plug in 0 for the house size into my equation. Price equals 50,000 plus 100 times 0 equals 50,000. So, yes, the model predicts a $50,000 price for a 0 square foot house. If the house size increases by 100, the price change is 100 times 100 equals 10,000. Therefore, a 100 square foot increase adds $10,000 to the price prediction. Absolutely. Linear regression, by its very nature, assumes a straight line relationship between the variables. This means the increase in price is consistent for each additional square foot of house size. This statement is false because outliers, unusual data points, can significantly skew the results of a linear regression model, affecting its accuracy across different house sizes. This is the title summarizing the topic we're exploring: using a linear regression model to predict house prices. It's a common application of this powerful statistical tool. Let's see. The model predicts a house price using the formula: house price equals 50,000 plus 100 asterisk house size, in square feet. If the house size is 0, then the predicted price is $50,000. This is the y-intercept of our model. That's what we'd get if we plugged in 0 for house size. Makes sense, right? I can explain this. The coefficient of 100 means for every additional 100 square feet, the predicted price increases by 100 times 100 equals $10,000. That's the slope of the line. It tells us how much the house price changes per square foot. Yep, linear regression always assumes a straight line relationship between the predictor variable, house size, and the outcome variable, house price. In simpler terms, the model expects a constant rate of change. As house size increases, the price increases steadily, proportionally. Not necessarily, VOMC. Outliers, exceptionally large or small values, can strongly skew linear regression results, causing inaccurate predictions. The model's accuracy depends heavily on the data quality. This equation shows how the model predicts a house's price. I'll explain this step by step. First, you take the size of the house, in square feet, and multiply it by 100. This is the effect of the house size. Then, you add 50,000 to that result. This 50,000 represents the base price, even for a 0 square foot house. It's like saying the base cost is $50,000, and every extra square foot adds $100 to the price. Pretty simple, right? If you plug in 0 for house size in the equation, you will get $50,000. This is true because the intercept, the constant term, of the linear regression equation represents the predicted value when the house size is 0. That's our base price. Let's test this. If you increase the house size by 100 square feet, the price increases by 100 times $100 equals $10,000. This also means the coefficient, 100, indicates how much the price changes with each increase in house size. So the statement is true. Linear regression always assumes that the relationship between the input variable, house size, and the output variable, house price, is linear. That's why it's called linear regression. It's right there in the name. This is false. Linear regression is very sensitive to outliers, extreme values. If the data used to train the model had some really large or small values, this would affect the model's accuracy and ability to predict values outside the range of the training data. Think of it like this: if you only train your model on large houses, it might not predict small houses accurately. This question sets the context. We're dealing with a linear regression model from Sklearn, which is a popular Python library for machine learning. We're given the key outputs from training the model on house size and price data. Sklearn is just the tool we're using. The core concepts are about linear regression itself. The intercept and coefficient are crucial for understanding the model's predictions.